can start. So today I'm delighted to introduce Whitney Behr, who's visiting us from UT Austin. Whitney originally was an undergrad at Cal State Northridge. Then she went to USC to do a Ph.D. supervised by another person named John Platt, which is an endless source of annoyance to me.
Also
It's also rude.
a little older than you, though.
Much older. And then following her Ph.D. at USC, you went to Brown as the departmental postdoc fellowship and branched out to start doing experimental measurements of rock deformation with Greg Hirth. And then has now been at UT Austin for 3 years now? And Whitney combined sort of experimental and field approaches to study lithospheric deformation. And today she's going to talk about constraints from Exhumed Rocks on strength and rheology of continents.
Great. Well, thanks, John, for the introduction, and thanks for the invitation. Nice to meet with several of you already. Right, so today I'm going to talk about some work I've been doing for the last several years that focuses on using exhumed rocks and deformed xenoliths to place constraints on strength in the continental lithosphere. And the motivation that or the question that motivates this aspect of my research is one that's remained unresolved for several decades. And that is, what is the magnitude of deviatoric stress at different depths within the continental lithosphere? In other words, how strong are the continents, and at what depth within them does the peak strength actually reside? And for several decades now, people have recognized that there are significant complexities that affect continental regions that do not affect oceans. For example, one of the most obvious is compositional stratification that we see in the continents. But along with this comes more complex geothermal and density gradients, as well as the effects of the protracted geologic history that most continents have been subject to that oceans have not. And this complexity in the sort of strength and rheology of the continental lithosphere manifests itself at the very large scale. So if we look, for example, at a current plate tectonic map of Earth, we see that oceanic plate boundaries are very discrete, very narrow, very plate-like, fairly simple kinematic patterns going across them, whereas wherever deformation is affecting continental regions, it's much more complex. We see deformations distributed several hundred kilometers inboard into the plate interior, and it's often very difficult to sort of choose a specific line that defines the plate boundary in continental regions. So in other words, continents are actually not particularly plate-like, and this is because of their more complex rheology at depth. This strength in the continental lithosphere also affects their stability, so just thinking at the sort of more regional scale and thinking of continents in cross-section. Their rigidity, or in particular the relative strengths of the lithospheric mantle with respect to the crust, controls their stability over time. So for example, there's these kind of classic models of a very weak mantle and a strong crust that's referred to as creme brulee because we all love food analogies. But basically that predicts that if you have a weak lithospheric mantle, then over time you're going to develop instabilities. The mantle lithosphere can actually sort of drip and sink into the underlying mantle, a xenospheric mantle. Whereas in the case of a strong mantle lithosphere, the model we refer to as jelly sandwich, we expect that the mantle lithosphere or the continental lithosphere will remain stable over longer time periods. It'll remain in compression over long time periods, and it can ultimately end up sort of acting much more stable or behaving more like cratonic continental cores, like we also see on Earth going back to the Archean. Other just quick things worth mentioning that continental strength affects is mountain building and topographic development, and this has become especially relevant for the development of the Colorado Plateau, where people argue, the Tibetan Plateau, where people argue there's been substantial lower crustal flow that helps to sort of smooth the topography there, and that's telling us we have a fairly weak lower crust there. And then even on human timescales, people have suggested that continental strength, or we know that continental strength is what controls seismicity in continental regions and therefore hazard. And people have even suggested that the magnitude frequency distribution of earthquakes, what we call B value, may control or may be controlled by the crustal strength profile. So the kind of key points is that constraining continental rheology and strength with depth is sort of a key aspect of geodynamics. So a variety of laboratory geophysical and geological techniques have gone toward trying to get at this issue of continental strength in the lithosphere. And my approach has been to develop and extend the ways that field geology, microstructural analysis, and various new analytical tools can be used to quantify strength in both the crust and the mantle. So today I'm going to sort of talk about exactly how I do that and give you a couple of case studies, one from the crust and one from the mantle, and show you some of the tools that we actually use to get at this. So to give you an outline of my talk, I'll start by talking about what inferences we normally make about lithospheric strength, which then form sort of a framework which we can use natural observations to test. Most of this is going to come from laboratory experiments. And then I'll talk about some of the techniques we can use in rocks to measure rheological properties and specific rheological parameters. And then I'll go through, like I said, a case study from the middle crust and from the lithospheric mantle. Both are from the western US and the Mojave region of eastern California. Okay, so when we talk about stress in the lithosphere, we're talking about the magnitude of deviatoric stress, or the sort of shear stress that rocks can sustain before they fail, either by brittle mechanisms or by ductile mechanisms, or frictional or viscous. And most of what we know about stress in the lithosphere initially, or what we think we know, comes from laboratory experiments. And these predict different relationships depending on whether the rocks are deforming in the brittle regime or the ductile regime. So for example, for the brittle field, we expect a fairly simple relationship that looks like this, where the shear stress is linearly related to the affected normal stress via a coefficient of friction known as mu. And we find from experiments that based on sort of a whole bunch of different rock types, mu tends to fall between 0.6 and 0.8. And so this predicts for the lithosphere, or the upper crust, that rock strength will increase linearly with depth. It's fairly simple, it's not temperature dependent, it's basically just dependent on confining pressure. Below the brittle ductile transition, when we start to get into the viscous regime, it gets a little bit more complicated. We have a bunch of additional variables, including a temperature dependence. It's an Arrhenius relationship, or an exponential dependence on temperature. Also got pressure in there. D represents grain size, FH2O represents water fugacity, and strain rate. And this predicts that in general, rock strength will actually decrease with depth in the lithosphere, mainly governed by the exponential dependence on temperature, and temperature is increasing. But rocks deformed at faster strain rates will be stronger than those deformed at slower strain rates. And then an additional critical variable that comes into play that's sort of not explicit in this equation is the rock type, or the mineral within that rock type, that we assume is actually controlling the strength at particular depths. So for example, I've plotted wet quartz up here for the middle crust. That's of course an assumption we have to make based on observation. But we may envision that the lower crust may be sort of depleted in quartz, may be more rich in feldspar, maybe pyroxenes, etc. So we might expect a different mineral controlling the rheology in the lower crust, and then we typically assume that olivine is controlling the rheology in the mantle. And then one additional set of variables that comes out in this equation that become also quite important is the value of this grain size exponent P and the stress exponent N. And these have a huge influence on our overall sort of integrated strength as well as our peak strength. So for example, for diffusion creep, where N is 1, so we have Newtonian viscous behavior, and we have a strong grain size dependence where P is equal to 3, for dry olivine, we would predict a curve for the mantle that looks something like this. Whereas for dislocation creep, where we have power law flow, no grain size dependence, we have a non-Newtonian viscosity, and we have a profile for the mantle for dry olivine dislocation creep that looks like this. These two predict really different relationships. They basically make the difference between jelly sandwich and creme brulee. So for example, dislocation creep is dominated, and then we're going to end up with this peak strength in the mantle, or at least for these particular parameters. We'll have a higher integrated strength, will be more jelly sandwich style model. Whereas if diffusion creep is dominated, we'll have a really weak mantle, we'll have this peak strength dominating in the crust, and creme brulee is a more suitable model. So you can see how just changing one of these many variables can lead to drastically different estimates of the overall strength and where the strength is controlled in the continent. And so you can imagine without constraints on these variables, then we're kind of lost as to what Christmas tree diagram, as these are called, or crustal strength envelope, or continental strength envelope actually applies to the real Earth. Fortunately, we can measure a lot of these parameters in natural rocks, and so I'll go through some of the examples of those right now. So pressure and temperature are some of the most obvious ones. We can get these from relationships from metamorphic petrology known as thermobarometry. And there are a whole range of them depending on which sort of rock types we're dealing with. The ones I've been using mainly in my lab include fairly simple ones. Try to stick with the easy stuff. Titanium and quartz thermobarometry is a relatively new thermobarometer that's great because it applies to quartz, which is a ubiquitous mineral in pretty much every crustal rock type that we can find, and it's based on the substitution for silica by titanium in the quartz crystal lattice. So that's a really nice way to get at PT in crustal rocks. And then for mantle rocks, they're a lot fewer, especially if the garnet is not involved, if you're just dealing with spinel facies, ferritites. But a common one is 2-pyroxene thermometry that's based on calcium and magnesium exchange between orthopyroxene and clinopyroxene. One thing I'll just point out on this slide is sort of the importance of texture or microstructural context for us when we're trying to understand deformation temperatures. So for example, this is a big porphyr class of orthopyroxene. A couple more of them sort of distributed here. This is a deformed rock. It's got a bunch of recrystallized grains surrounding those porphyr clasts. And we see different mineral chemistries associated with the porphyr clast, like shown here in red. In this case, I'm just showing aluminum contents in orthopyroxene, versus the recrystallized grains shown here in blue, as well as the cores of the porphyr clast. This is telling us a lot of times rocks will record for several temperatures representing different events. And so when we're interested in deformation temperature, we're really looking at sort of the recrystallized grains to get at that, as opposed to the earlier history recorded by the porphyr clast, the relic grains that recorded sort of different temperature conditions. We can also fortunately get at deformation mechanism, so basically get at the stress exponent n as well. I didn't put it here, but the grain size exponent as well, based on microstructural observations. And just to give an example, one of the things that tells us a lot about whether dislocation creep versus diffusion creep is active is lattice preferred orientations. And this is an example from the Whipple Mountains, which I'll talk about a little bit more later, but here's a shear zone cutting through. This is sort of a quartz-rich granitoid. You can see that shear zone here, and we use electron backscatter diffraction to get at the orientations of the grains within that shear zone. We plot them up and we see they're all clustered. When they're clustered, that's telling us that we have a lattice preferred orientation, and that tells us that our n, sorry it got cut off there, but our n would be power law, so 3 to 4 as opposed to 1. When we see deformation fabrics that don't have an LBO, we start to look at other mechanisms, and we're more likely to be, or those are more likely to represent diffusion creep or Newtonian viscous behavior. We can also get at the parameter we're most interested in itself directly, the stress magnitude, based on a relationship that's taken from, or originally from metallurgy, that's based on recrystallized grain size. It's known as paleopiezometry. And this is an almost inverse linear relationship between the recrystallized grain size and the flow stress. The relationships for many minerals, many metals, steel, for example, minerals, quartz, olivine, calcite, dolomite, all show this kind of relationship, so that at high stress magnitudes, where the rocks are really strong and cold, they're going to show very, very small recrystallized grain sizes. And at low stress magnitudes, where the rocks are warm and weak, they're going to show very large recrystallized grain sizes. Furthermore, again, kind of emphasizing the role of texture, we'll see different textures associated with those recrystallization regimes. So for example, at low stress and high temperature conditions, we see these very coarse grains. The grain size distribution is very broad, and the grains themselves have this amoeboid shape to them. We actually refer to them as amoeboid grains. Whereas at high stress and low temperature conditions, we'll have those porphyr clasts again with very tiny, sutured, very irregular but very uniform grain size recrystallized grains along their margins. And then in the intermediate case, sort of moderate stress and moderate temperature, we'll see what we call a core and mantle structure. We get these long grains that are stretched out that then have sort of fairly equant, medium-sized recrystallized grains surrounding them. So right away we can just take a look at a thin section or a texture and have an idea of whether we're dealing with sort of high stress, low temperature rocks versus low stress, high temperature. So it's kind of a qualitative measure, but then we can quantify it using these empirically derived piezometers. Yeah?
How did you know what the stress was on those conditions?
So that comes from an empirical piezometer. So if we want to know the exact stress, then we have to apply the piezometer itself. And these are there are some theoretical calibrations as well as empirical ones. I tend to use the empirical ones because I think they're better constrained. And they're done over the stress conditions that we actually expect in the Earth, so there's not a huge extrapolation. But so, for example, if I have a a recrystallized grain size of 5 microns, then my stress magnitude is going to be about 200 megapascals. Yeah, please feel free to stop me for questions, especially because I talk really fast. One other thing that we can calculate is the water measure, I should say, is water fugacity, or at least the sort of water content in nominally anhydrous minerals. And most of these are very dry, of course, but we can measure the water that's actually dissolved in the crystal lattice using both, in my lab we use both FTIR and SIMS to get at that. So the take-home message is that we can start to sort of place natural constraints on these parameters and build a database for individual regions or individual sort of continental areas and start to use them to start to test some of these sort of framework assumptions from laboratory experiments. An example of questions we can answer, for example, is, are the magnitudes of stress that are recorded in natural rocks in the crust actually consistent with Byerlee's law? So if we can identify rocks that come from the brittle ductile transition, do they actually yield this stress magnitude? Do natural rocks show the predicted exponential decay in stress with depth that we expect from an Arrhenius dependence on temperature? It's another question we can get at. And then we can start to kind of, on a regional basis, or case-by-case basis, say something about which layers in the continents yield the highest stress magnitude. So not only distinguishing between jelly sandwich and creme brulee, but also getting an idea of where the peak strength resides in here, as well as the integrated strength, and finding out sort of what end members between these two. These are two extremes, but what really applies in between them to particular regions. Okay, so I'd like to take you through a case study where we were able to look at this for crustal rocks and sort of look at what happens in the mid-crust where quartz is a dominating lithology. And I'll be showing you some examples from the Whipple Mountains core complex where we were able to look at the footwall and sort of identify different fabrics formed at different conditions that allow us to constrain or produce a naturally constrained stress profile, and then use it to answer the questions I posed on the last slide. So this is the Whipple detachment itself. These are tertiary, basically surface volcanic rocks, and underneath them are sheared granitoids brought up from about 10 kilometers depth, juxtaposed against these surface deposited basalts. So the Whipples are in the easternmost California on the border with Arizona, and they represent, like I mentioned, sort of a metamorphic core complex. This is the detachment itself. It's very dome-like now, and it's exhumed a stack of primarily myelinitic rocks, highly sheared myelinites and gneisses, mainly granites, granitic in composition, from 10 kilometers depth. And the hope is that if we can identify different domains within this footwall where rocks are deformed sort of maybe deeper in the middle crust, a little bit shallower, and then ultimately at the brittle ductile transition, then we can create this strength profile. So what I mean by that is, especially if we can take into account the tectonic history of the region, which core complex models, some of you may be familiar with the rolling hinge model of the core complex. Well, this was invented or designed based on the Whipple Mountains history. And so the way it works, you have sort of incipient extension occurring in the mid-crust. This is basin and range age. And you can envision that sort of early on in the extensional history, you have rocks deep in the middle crust that are deforming by viscous flow. And those early fabrics, if we can identify them, would represent a stress depth point that's way down here. But then as the rocks start to get captured along this detachment and you start to get more extension, they'll get overprinted by more localized ductile shear as they approach the brittle ductile transition. So sort of the ductile roots of that brittle detachment will overprint some of these earlier formed higher temperature rocks. Those might represent a sort of intermediate condition here. And then eventually you continue to bring that footwall up and exhume those rocks. You exhume them through the brittle ductile transition. They record their highest stress magnitudes right in the middle crust before they cease to deform viscously and just deform brittly. And so those would represent a point right here. Fortunately, metamorphic core complexes lend themselves really well to preserving these because the deformation becomes more and more localized over time. You start out really distributed flow, it gets more localized, and eventually becomes localized onto basically just the discrete brittle fraction or brittle faults in the upper crust. So I'll show you some examples of what these different fabrics look like. So here's an example of a low stress, high temperature myelinite zone. There's basically a distributed stack of myelinitic gneisses. And these show both qualitative and quantitative evidence of having formed under amphibolite facies conditions. And this is what they look like. It's like what I had on my title slide. They're basically what's referred to as algan gneiss. They have these sort of are quartz-rich dikes that have been stretched out. And then these are feldspar porphyroclasts that are very rounded because they're partially recrystallized along their margins. The dark material is biotite, which is present and stable. There's no chlorite, so that's one of the hints that tells us this is a high temperature sort of amphibolite facies rock as opposed to green schist facies. We also, this recrystallization in feldspar tells us that we're above about 450. We see sort of high temperature quartz microstructures. And then when we look, lattice preferred orientations or CPOs. And then when we look at the quartz microstructure, we see something that looks like this. Basically, it looks like that low stress, high temperature cartoon that I showed earlier with these highly irregular, very coarse grained, but very amoeboid looking, and this significant grain size distribution associated with those. And again, you can see all this stable biotite, no chlorite developing around it. So both, and also the titanium and quartz from this gives us amphibolite facies temperature. So both qualitative and quantitative evidence tells us these are low stress, high temperature features. At the intermediate side, we see rocks that look more like this. So this is looking down on a foliation plane. This is a myelinized granitoid. And we see this streaking, which represents a stretching lineation where quartz is pulled out ductilely. But then the feldspar, instead of forming those nice rounded algan, is forming these little kind of blocks, very blocky and tabular, and they've basically been broken up brittly along their cleavage planes as opposed to stretched or recrystallized like they were in the other rocks. And so in these rocks, we see biotite partially retrogressed. We see this brittle deformation in feldspar as opposed to ductile. We still see the same lattice preferred orientation, but our quartz grain sizes are much different. They look more like this. They're much smaller. Those other ones were over 150 microns. These are more like sort of 60 microns, fairly equant and fairly uniform in size. And then finally, at the other end of the spectrum, where we're expecting these rocks to basically be crossing through the brittle ductile transition, we see features like this. This is a brittle slip surface. It actually has a small amount of pseudotactylite along it. And then there's a ductile shear zone, however, that kind of goes in and out, as if this started as a ductile shear zone and culminated in brittle flow and eventually melting. And so this is a kind of characteristic feature that would tell us that we're near the brittle ductile transition in these rocks. Those type of rocks show biotite retrogressed to chlorite. Again, they show this brittle deformation of feldspar. The lattice preferred orientation in quartz gets changed to basal shear, which is more typical of cold temperatures. And then, of course, we see really fine recrystallized grain sizes, often difficult to resolve at the optical scale, so we use electron backscatter diffraction to get them. You can see these long porphyroclast grains and then these tiny pockets of recrystallized grains around them. These are on the order of 7 or 8 micron grain sizes.
Whitney, how much, what's the water content of these 3 different end members? Or, you know,
so all of them have lots of fluid inclusions, and we assume we're pretty much all at lithostatic fluid pressures and high water contents.
Okay.
So the main point is we see this sort of progressive, or this spectrum of quartz microstructures that represent different stress temperature conditions, from the low stress, high temperature end to the very high stress, low temperature end. So when we plot those up, this is what we see. So these are all of our data, starting from the low stress myelinitic gneisses all the way up to the brittle ductile transition type of features. And right away we see some things that are kind of promising. For one thing, we see that the peak ambient stresses in the mid-crust seem to fit with Byerlee's law, so they and hydrostatic pore fluid pressures. And then we also see that sort of expected decay, exponential decay in stress with depth that we expect from the experiments. So at least for the Whipple Mountains, we seem to see kind of exactly what we expect to see from these laboratory-derived relationships, which is fairly encouraging.
Can I just ask, how can you be sure there hasn't been some post-extensional recrystallization going on in these rocks?
So, do you mean annealing or?
Well, annealing of the system,
Yeah. So I mean, annealing is really easy to recognize microstructurally, because you'll see the grain boundaries readjust to form low energy configurations that are like 120-degree triple junctions. And we don't see any of that here. And then, I mean, that's one of the things that's really nice about extensional terrains is they're getting colder with time, so they're actually getting quenched as they're being exhumed. And especially once they go into the brittle field, as long as we ignore, you know, the brittle clay sites and things that cut them, they're just frozen in place.
I guess naively I would know expect extension and uplift happening at the same time.
Well, there's a lot of, there's exhumation, but in terms of surface uplift, there probably isn't a lot here. It's actually thinning and exhumation. But the thing is, the point about extensional terrains is doing the opposite in thrust terrains is much harder because you're actually burying your earlier fabrics and your deformation is getting wider and wider, and you're getting hotter so you can anneal them much more easily. Okay, so more recently I became curious as to whether this relationship that we see in the Whipples might actually apply more globally. And so since 2011, when John Platt and I published that paper, this sort of technique has been applied to several other places, and there were also places where there was data from previous studies. So I compiled all of these data together from both basically 58 measurements of this paleopiezometry dynamic recrystallized grain size in quartz and calcite from 21 different studies, about 10 of which have been published in the last 5 or 6 years. And the areas that are included in the compilation are port complexes in the Basin Range, of course, like the Whipples, but also the Alps and the Mediterranean, exhumed thrust belts in Scotland, Taiwan, and the western US, as well as a couple of strike slip faults from Tibet, the Italian Alps, and the western US. And here's what that compilation ends up looking like. So this is the raw data on the left side, and this is kind of a summary of just a cartoon of what those data show on the right side. And again, we see pretty much what we would expect to see. So first of all, these are plotted, the colors are based on geothermal gradient. So the hot geotherms are in red, and the cold geotherm is in blue, and this was based on what people had published for their PT data. And we see what we expect to see, that the brittle ductile transition in the high geotherm is shallowest, where in the cold geotherm it's deepest, so that's what we expect. We also see the sort of, for all three geotherms, the characteristic decay, exponential decay with depth that we expect from the Arrhenius dependence on temperature. And then for the hot and intermediate geotherms, the red and yellow, we see again that they overlap fairly well with what we expect for Byerlee's law under hydrostatic pore fluid pressure. We don't see that showing up very well for this coldest regime, but that gets back to what I just mentioned before, that that preservation of sort of cold geothermal gradients from brittle ductile transition are really rare, because the process that actually brings them to the surface increases temperature and advex heat. So you're actually very rarely going to see sort of cold geotherms exhuming through the brittle ductile transition. So it's kind of a sampling bias in a sense that we're not able to sample these because as they get toward the surface to where we can see them, their geothermal gradient increases. So again, kind of good news that global compilation seems to fit what we expect for, or based on laboratory flow laws for strength distribution with depth. That said, though, one of the other purposes, oh, sorry, I'll get to that in a second. Just want to point out that we can look at these data in a different way. We can basically plot them in terms of temperature and stress, so those are all measured parameters. We can plot them alongside quartzite flow laws, which also characterize temperature and stress at particular strain rates. And what we find is the most recent quartzite flow laws bracket these data for geologically reasonable strain rates. Geologically reasonable meaning strain rates measured using GPS, strain rates measured using estimates of velocity across shear zone width, for example. Paleoseismology all gives estimates of strain rates that are geologically reasonable for steady state conditions of about 10 to the minus 11 to 10 to the minus 15. And we see these data are nicely bracketed. So again, that's an independent sort of comparison telling us that quartzite flow laws are doing a pretty good job of predicting the relationship or the stress distribution at depth in the crust. Okay, so that all said, another purpose of this paper that John and I wrote in 2014 was to also think about the implications of these data for faults and the strength on faults. And so we wanted to look at, okay, what do brittle faults look like? And let's also compile those and compare them to what we get for the middle crust. So we put together 15 estimates of, these are published estimates of static stress magnitudes. We're not looking at dynamic stresses at all, just static, from 14 different studies on different normal thrust and strike slip faults, and a lot of different methods that come up with sort of static stress magnitude. And what we find is even though our ductile sort of microstructures and our paleopiezometry from the middle crust seem to fit Byerlee's law, all of the stress magnitudes for brittle faults are much weaker. They don't actually fit Byerlee's law. It's sort of dichotomous that brittle faults seem to be much weaker than Byerlee's law, whereas the middle crust seems to be exactly the right strength compared to Byerlee's law.
Is that because you're getting repeated movement along those faults and you've got accumulated strains that are not from single events?
So I don't think so, because the ductile shear zones we're looking at are really high strain features. And so none of them actually directly correlate to the brittle faults that we looked at, but they represent the ductile roots of very long-lived, high displacement brittle faults. So for example, the Whipple detachment has 40 kilometers of displacement on it. And most of these ones that are developed as big myelinite zones, another example is like the Karakoram fault is one of the ones that we have calcite piezometry from. So these are big shear zones that represent big, large displacement brittle faults in the upper crust. Does that make sense?
I think so.
Yeah.
Yeah. How do you calculate depth once you're in the brittle regime for this plot?
Depth?
Depth.
A bunch of different, a lot of them are estimated from, the source of earthquakes, for example, and then some of them are experiments on natural fault gouge actually come from SAFOD, the drill holes. So in some cases they're actually directly sampling from particular depths, especially these shallow ones within 5 kilometers or boreholes.
Okay.
So they'll extract that and then measure the coefficient of friction. But it's a bunch of different methods, and some of them, yeah, you can see have gigantic error bars in like this one way down here. Their depth resolution was really poor, but the error bars represent the estimated depth resolution that people in that particular study were able to were guessed at.
But for the ductile regime samples, you're still using the 2-pyroxene.
Oh, so for the ductile ones, yeah, I didn't talk about it too much, but especially in the case of, so most of these were assuming a geothermal gradient, a steady state geotherm like this, but for the Whipple one, we actually used a thermal model that sort of represents extension of the crust. So it's not quite a steady state geotherm because it was advecting heat upward, but most of these were just assuming a geotherm within 10 degrees. Okay, so like I mentioned, we have this discrepancy where the middle crust seems to be strong, the upper brittle crust seems to be weak. And there are a lot of weakening mechanisms that have been proposed for the upper crust. For example, high pore fluid pressures, an abundance of clay minerals. People have argued as well that you can get coalescence of micas into interconnected weak layers, and that can precipitate or facilitate pressure solution and sort of weaker mechanisms than dislocation creep. But no matter what the weakening mechanisms are, we want to reconcile this data set where we have sort of a very strong middle crust and a weak upper crust, then we need to have an abrupt downward termination in those weakening mechanisms just above the brittle ductile transition. So for example, we envision that you might have low effective frictional strength in the upper crust on these sort of high displacement faults that have maybe clay minerals that are weak. Those clays may break down, however, to generate or to lead into high effective frictional strength before we end up in this sort of high strength crustal beam, basically in the middle crust. Otherwise, we would expect deformation to continue and be brittle and not formed by dislocation creep all the way through the middle crust, because you can accommodate stress, or lower stresses that way. So we kind of proposed that, and this is stuff that definitely needs to be tested in more detail, but we think this transition is likely controlled by temperature, and that causes the instability of clay minerals above about 260 degrees, whereas quartz becomes viscous at about 300 to 350, so there's sort of maybe a kilometer, depending on the geotherm, or 40 degrees C of temperature where you're transitioning from sort of weak to strong. There's also a lot of places that show evidence for a process known as precipitation hardening, or basically injecting veins and then bringing in harder minerals, feldspar, epidote, for example, that are much stronger than clays and that can strengthen faults just above the brittle ductile transition. And then another case, at least in sort of phyllosilicate poor assemblages, they don't interconnect into these weak lenses in some places. All stuff that needs to be tested in more detail, but it's kind of the only way, it's a prediction that we get from trying to reconcile these two data sets. Just to mention that the implications of this are fairly important. For one thing, they suggest a much lower integrated strength for the crust than you would expect if Byerlee's law were controlling the whole strength. So it helps get away from sort of the heat flow paradigm. But also it tells us that the middle crust is really what's driving everything in the upper crust, that as opposed to sort of boundary forces being applied to these faults, they're actually being driven from below by basal shear stresses in this strong mid-crustal layer, this sort of M zone. So that's kind of most consistent. Anyone who's familiar with sort of geodetic models, it's consistent with the more classic Savage and Burford elastic dislocation models. Okay, so does anyone have questions? I was going to move on to the mantle. Okay. Okay.
Thought you'd never get there.
You're awake now. All right. Okay, so hopefully I've convinced you that we have some interesting sort of good news and bad news for the middle crust. And now I'd like to move on to thinking about the mantle lithosphere. And when we want to sort of investigate the mantle, we have two options. There are continental mantle massifs, which are not terribly common, but there are some, especially in hyperextended continental margins. There's lots of them in the Alps. There's some in southern Spain. There's continental mantle massifs are around, but they tend to be difficult to work on because as they get exhumed through the crust, they tend to get serpentinized and get significantly overprinted. So the other option we can use is mantle xenoliths, which are sourced from basically sample fragments sourced from volcanoes. And this is sort of my preference because they're often very pristine. They are plucked directly in situ from the mantle and brought up very rapidly to the surface, so they don't have time to reset their steady state fabrics. This is an example not from anywhere that I've worked. This I stole from the internet, but this is Hawaii, beautiful basalt with hundreds of mantle xenoliths, and this is what they often look like. And so I've been working on a wide range of these to try to get at some of the same issues I was talking about in the crust, basically mantle rheology and mantle behavior. So the ones I'll talk about today come from the Mojave region, and this is part of what's referred to as the Eastern California Shear Zone. This is an active transtensional zone associated with the San Andreas Fault. Mojave region is basically south of the Garlock Fault. It represents this sort of triangle here. And I'll talk about samples coming from both the Sima volcanic field as well as Dish Hill, but there are a few others that are sampled a little bit west of some of these faults highlighted in pink here, which I'll talk about in a moment. Just to show some pretty pictures, these are a couple of the volcanoes in the Sima volcanic field. This is my personal favorite. It's often referred to on the internet as Huell Hauser's supervillain volcano layer because he built this house up on the top of the anyway, he donated it actually as a field station to Chapman College in California, so that's a pretty sweet field station. I haven't gotten there, but I will one day. So the xenoliths that are sourced from here are derived from both the Spinel peridotite stability field as well as the plagioclase stability field. So the plagioclase ones are much shallower. The Spinel ones can go down to about 70 kilometers. So far we've only found them down to about 50, but there may be some from hotter. And it also includes lower crustal xenoliths that tell us that definitely seem to be related to lower crustal sort of magmatic underplating associated with the same volcanism that has now made it to the surface and formed a whole bunch of hundreds of basaltic vents within the Sima field and a few in Dish Hill. And so these provide kind of a nice column, lithosphere column, through at least sort of 25 kilometers or so down to about 50. And they also have a little bit of a spatial dimension to them because they're sourced from different regions. So it's not just one point source, but we're looking at several from here and several from here that are spaced about 150 kilometers apart. So we get a little bit of information about spatial heterogeneity as opposed to just one point in the mantle. So we can again come back to this and we can use the xenoliths to constrain a bunch of these rheological parameters in natural rocks. So water fugacity, stress, magnitude, temperature, pressure, etc. So I'll go through and show you some of those. So these were actually from, this one I showed earlier is actually from the Sima volcanic field. And from 2 pyroxene thermometry, we get temperatures ranging from 880 to 1050. Sorry, that's missing there. And like I said, we're very careful to distinguish, whenever I say these temperatures, I'm talking about the deformation temperature represented by the recrystallized grains as opposed to the host porphyr class that clearly record higher temperatures and represent cooling. And then pressure is a little bit trickier, but fortunately, since we have some plagioclase-bearing prototypes, we can say something about the geothermal gradient here. So for example, we know this plagioclase to spinel reaction boundary in prototypes fairly well. It's basically here. And we have all of our plagioclase-bearing samples have temperature ranges from about 850 to about 960 or so. So that's this green box. And that overlaps. We also have independent constraints on sort of the geotherm within ranges here from both seismic attenuation from data from Young and Forsyth, as well as crustal heat flow from a paper by Williams and others. And so we can see that our plagioclase xenoliths, given this constraint on the plagioclase spinel boundary, only overlap with the hottest geotherm for both the crust and the mantle. So we know then that we're dealing with pretty hot mantle lithosphere here, and in fact that was actually the preferred model from Young and Forsyth as well. So then when we have spinel xenoliths, we're basically just using this hot geotherm to figure out what depth or estimate what depth they come from. We have samples that look like this. These are basically high temperature myelinitic peridotite, and they have very characteristic dislocation creep type of textures. So here's a big porphyr class, there are crystallized grains all around it. You can see subgrains developing, that's telling us about dislocation activity. This one's sort of a tectonite, whereas this one's much higher strain and would be referred to as a myelinite. You can see those porphyr class again. And they have strong lattice preferred orientations, which tell us, again, that we're dealing with dislocation creep and a high stress exponent, so it's power law behavior. Also, the fact we talked earlier about this annealing, there's no annealing or low energy configurations here. And that tells us that these are very young fabrics that they represent, because these are hot rocks, and in order to not have any annealing associated with those high temperatures means that these have to be very youthful. We've done some calculations, basically less than 3 billion years old. The lower crustal xenoliths also show evidence for dislocation creep, where so we have a lot of undeformed gabbros that have plagioclase and pyroxene and amphibole in them, but where they're deformed, they show clear dislocation creep in plagioclase with strong lattice preferred orientations, and plagioclase is actually dominating the rheology here. Water contents are fairly low, but they're still measurable, so we kind of refer to it as a damp rheology, and again, we're interested in paying attention to texture because we find a lot of the really large pyroxene porphyr class have core to rim zoning within water. So we know that there's also not only a temperature history here, but a hydration history that gets preserved with these going from wet and becoming more dry. We did it using both FTIR and SIMS and get pretty good agreement on those with sort of wet pyroxenes and fairly low ppm water and olivine. And then finally, we can use the recrystallized grain sizes as well as the subgrain sizes to get at this differential stress using the piezometer for olivine, which is what this is showing. So differential stress here, recrystallized grain size. Now recrystallized grain sizes in this case are very large, basically 400 microns or so, which gives us stress magnitudes of 15 to 18 megapascals. So despite that these are fairly dry and deforming by dislocation creep, they're still very weak. So we can do the same thing that we did before and try to plot this on a stress depth diagram and start to kind of build a more lithospheric scale strength profile. So these are green are samples from the Sima volcanic field, and red are from both Dish Hill and Sima, two different papers, long story. And we see fairly low stresses in the mantle here, represented by those. And although we don't have samples from way down here at sort of 50 to 60 kilometers, I plotted here the stress range and basin and range xenoliths that are sourced from this depth range. And so you can see there is an exponential decay with depth, again, to very, very low stresses at the very deep parts of the mantle lithosphere here. So those are the raw data. Then we can plot olivine flow laws superimposed on that using all those parameters or plugging in all those parameters like water content and stress magnitude and pressure and temperature conditions. And so these are the stresses predicted from olivine flow laws. And again, we find that the strain rates estimated here, 10 to the minus 13 to 10 to the minus 14, are exactly within sort of a natural range we would expect for the mantle, and especially for this region where we actually have geodetic estimates of strain rate which are on that order of magnitude. So then if we want to compare this to the rest of the crust, we have lots of sort of evidence of discontinuities in the Mojave lithosphere thanks to the wealth of geophysical data. So we know where the moho is very precisely, basically at 28 kilometers from receiver functions. We know that there's this lower crust to middle crust transition at about 22 kilometers from magnetic data. And then we know the brittle ductile transition based on the base of the seismogenic layer there. And so we know that depth as well. So we can get a lot of these transitions here. And we can start to build sort of a Christmas tree diagram for the whole lithosphere. So for the lower crust, we only have samples that come from basically about here in the xenoliths, unfortunately. But we can still place some general constraints on, and minimum constraints on what the lower crustal strength will look like. So for example, we have gabbros. We know that at max they have 50% diopside based on measuring sort of hundreds of them. But then where they're actually deformed, so where they're deforming at fast strain rates, for example, that deformation is accommodated by anorthite. And so we know that this is kind of the maximum strength curve if they're kind of undeformed and deforming slowly, and this is the minimum strength curve if they're deformed and deforming quickly. So where deformation is localized, there'll be this strength, and where it's just host rock, it'll be this strength. Right away, you can see even our minimum predictions suggest much higher stresses, peak stresses in the lower crust than we would see for the mantle. And then the middle crust, we actually have a constraint on the upper crust based on the Cajon Pass borehole, which is also from the Mojave, and that suggests the deformation, or the crust there follows Byerly's law. And we can plot quartzite flow laws here, but this profile is also consistent with what we see for the nearby Whipple Mountains, also in the Mojave region. So we have a strong middle crust, as we sort of already constrained, as well as a strong lower crust. This middle section here is very difficult to constrain. Is probably our hardest to figure out what's going on at the transition from quartz-dominated to feldspar-dominated. But the main take-home message is we have a much stronger crust here than we do a mantle, suggesting we're dealing with a sort of creme brulee type of model, at least for the Mojave region. Okay, so I just want to mention really quickly that we can compare this information to a wealth of other geophysical data that's tried to get at crustal and mantle rheology for the lithosphere here. And most of those are based on post-seismic relaxation for the Landers and Hector Mine earthquakes, which occurred in the 1990s. And just to give you a couple of examples, these were both pretty high-impact papers after those earthquakes. And this early one by Fred Pollitt suggested that the mantle lithosphere here is deforming by linear viscous creep, whereas a later paper by Friedrich Bergman that sort of had longer time series suggested power law flow. Ours xenolith data constrain this based on the fact that all of our fabrics show lattice preferred orientations and show evidence for dislocation creep. So ours are only consistent with this later model. But all of the models required a very hot geothermal gradient on the order of what we get from the xenoliths, and all of them predicted much lower effective viscosities in the upper mantle than in the lower crust. So for example, we can actually quantify that. These are the ranges of viscosities that are measured from not just post-seismic relaxation, but also post-glacial rebound for the Mojave region. And you can see the lower crustal viscosities end up an order of magnitude or two larger. This is the mean, the red, and this is the range in gray. And we can also plot our data here just using the relationship where viscosity is proportional to the stress divided by the strain rate. And these are what our results look like. So here's our lower crustal strength that overlaps fairly nicely. Here's our uppermost mantle, as well as the lowermost lithospheric mantle anyway, from the basin and range suites. And in both cases, we see ours are stronger, but that makes sense because we're dealing with deformation on timescales of 3 million years or so, sort of the true steady state, whereas all of these post-seismic studies and post-glacial rebound are actually evolving towards steady state and still represent transient viscosities that are always going to be higher and eventually settle on a steady state magnitude. They're also averaging over a much larger depth range, whereas we're able to kind of at least constrain individual parts of the mantle lithosphere. Okay, so the take-home messages, exhumed rocks can be used to make, or to test extrapolations from experimental rock mechanics and They suggest that brittle faults are weak in the upper crust, whereas the middle crust is quite strong. And the middle crust predicts sort of the exponential decay of the middle crust that we expect from experiments. And then xenoliths give us a lot of information about rheology and strength of the lithospheric mantle. I'll just thank the other John Flatt and my current PhD student Rachel Bernard and Greg Hirth and funding sources NSF and the Jackson School. Thanks.
Brad?
Yeah, so with the strength profile you're getting in the mantle that you're showing at the end, what's causing the strength to be so low?
Yeah, that's a great question. I meant to mention that. So partly it's the high geotherm, which is hotter here than many, say, cratonic regions, for example. But I think the other part is actually some melt weakening that might be going in there. And I think it actually has the effect, most of the melt actually travels through the mantle and then crystallizes in the lower crust. And I think it actually has the effect that it weakens the mantle, but then actually strengthens the lower crust by bringing in sort of new rock that's undeformed, that's much coarser grained. Now that's a great question of why it actually localizes there and why it's so weak. Yeah.
So that leads me to ask the follow-on question, which is when you have a sample that's plucked out by magnetism, right?
Yeah.
It's by definition coming from a wall rock, and the
Yes.
magma's going through.
Yeah.
How can you detangle the effect of weakening at that interface from the static, conditions
Process,
of the mantle
yeah.
before it was plucked? Okay,
So
that's really
one of the
difficult.
ways is the plagioclase itself, and these reactions to plagioclase, and the fact that then the plagioclase itself is deformed. So it's not completely agreed on, but most of the time the reaction from spinel to plagioclase is associated with melt, and then the plagioclase peridotites are deformed. So basically we're seeing melt infiltrating, the whole material is getting kind of exhumed because you're thinning the lithosphere there, and then you're deforming it. So wherever we see the deformed plagioclase peridotites, that's a hint that we're probably dealing with melt associated with deformation. There's also some examples of that Howard Wilshire described here. Unfortunately, I haven't been able to get my hands on them, where he describes dikes that come in and then start to get sort of sheared along their margins. So there is some evidence for melt weakening that's on the scale, long time scales as opposed to just the magmatic entrainment time scale.
So when you're making your measurements, primarily in the crust, for temperature of deformation using the thermometers, I missed it. How do you know that the temperatures that you're measuring correspond to the temperatures of deformation in the samples? What's the linchpin there?
So the main thing is if we look at only the recrystallized grains, with the idea that the recrystallization is a much faster way to reset the compositions than just like letting them sit there, for example. So the porphyr class will often show relict chemistries that represent much higher temperatures than what we get from the surrounding recrystallization. Basically, the deformation process distinctly enhances the kinetics, the reaction kinetics, and the diffusion time and length scale. So you're not dealing with static diffusion anymore, you're dealing with sort of pipe diffusion through dislocations. It's much faster, much easier to reset the grains.
Do you think deformation that you're seeing within one rock occurs essentially at one temperature, or is it a range of temperatures that work?
So I think it's a range, especially those Whipple samples really are showing a range, but we're able, using field relationships especially, we can actually see what represents a later fabric superimposed on an earlier one and sample from one of those, for example, cross-cutting shear zones that we know is late, and then only look at the temperatures associated with that particular zone. The xenoliths, it's harder for sure. So yeah.
Can you correlate the stress field you're observing in these systems with any sort of like mafic magmatic compositions? So maybe if you could go to a place where you don't have good constraint this from the metamorphic systems, you might be able to constrain it based on the magmatic compositions.
Oh yeah, that's a good question. I don't know if you could directly, but you could infer that if you have a continental mantle that has basaltic volcanism, it's probably going to yield a similar strength in the mantle, weakness in the mantle. Or where the geotherm is the same, you're going to end up with fairly weak mantle. So you can do it in that sense, that places that are tectonically active that have basaltic volcanism probably look like this.
you know, maybe people are already doing this, but it strikes me that these type of techniques, if you had enough preservation in the rock texture, you might be able to go back into the Archean, the Mesoarchean, and look and see at a time when radioactivity was higher, and look and see if the, you know, the extra heat coming from that radioactivity creates a different set of behavior regimes that would give you a weaker crust. Are you thinking about doing any of that kind of
I
stuff?
haven't thought as far back as the Archean at all, but I've been doing this for the whole Western U.S. with kind of that idea in mind that, you know, to what extent do we preserve these young fabrics? To what extent do the host rocks that aren't deformed still preserve some relic anisotropy, for example? So I was telling Chris earlier that, for example, the San Carlos volcanic field in Arizona represents completely annealed, you know, gem quality olivine, and yet if you measure it using EBSD, it has a lattice preferred orientation. So there is this fossil anisotropy and fossil history there. And so I've been interested from that point of view, but really only going back over the tertiary and looking at xenoliths that are oligocene from the Colorado Plateau, for example, that record the flat slab. These record San Andreas related deformation. San Carlos is basin arrayed, you know, so thinking of it on that time scale, going back much farther, you probably could, at least for the Archean crust, probably could do it. It would be interesting.
Can you do the same techniques? I guess basically, are there xenoliths from the mantle from colder regions where you might see a higher strength, or do you kind of need the high geotherm to have volcanism xenoliths?
Yeah, I mean, on the whole, most volcanism seems to be associated with this type of continental terrain, but I mentioned the Colorado Plateau, and that was a unique situation where once the Fairlawn slab fell away, you actually heated up the base of the hydrated mantle lithosphere and then erupted a whole bunch of volcanoes to the surface at about 35 MA. And those are sampling, you know, cold, not quite cratonic, but sort of slab-affected cold lithosphere. And yes, they're much stronger, for sure. I mean, the olivine there, stresses are 180 megapascals, but temperatures are 550 to 700. So they're much colder, wetter, but stronger.
Couldn't you go to kimberlites and things where presumably that?
Yeah.
That's pretty low geotherm in those areas. They just have to come up through plutonic regions.
Yeah, it's kind of weird though, because most of the xenoliths that come up there are actually very, very hot, like 1400 degrees, 1300 degrees, and very, very strained. And that actually kind of suggests that the deformation in them is some sort of a stenospheric type of process. Like I think maybe they do sample the colder part of the lithosphere that they come through, but the ones I've looked at that are deformed are really high temperature, much higher than this, basically.
So the latest work on water content in these olivines and these kind of xenoliths shows that they're all overprinted by metasomatism, and if you compare them to olivine inclusions in diamonds, which are probably older,
Yeah.
they're much drier. This is data of the last year. People started to look at the water content of olivine in the diamonds and suggest that, you know, at some point, maybe in the Archean, when there was original depletion, the degree of water that's been taken out is really extreme, and that what you see in the xenoliths now could either be a combination of transport, you know, from the kimberlite, or a combination of integrated metasomatism since the original depletion. That's
Yeah,
the kind of
I mean, in
emerging.
here there's lots of candidates for hydrous metasomatism. I mean, the laramide slab is a clear example. A lot of people have argued these particular xenoliths show duplexing kind of based on geochemistry. There's no real microstructural evidence for it, but so we know that this area of the Mojave interacted with the slab. And so that's what I think, like those pyroxenes that are zoned with high water contents in the core and, you know, drier on the rim probably represent that history. Could be earlier, but, you know, it's easier to think of it as, yeah, laramide came through and now it's been drying out ever since.
Anyone else? Thanks, Whitney.
Thanks for all your questions.